Welcome back. So in the last two classes, we started understanding some fundamental spin physics responsible for understanding NMR spectroscopy, especially 1 and 2 dimensional NMR and its applications. In the last class, I introduced you about spin angular momentum P, whose direction I said was quantized along z-axis Pz. I also said Pz is equal to m into h cross. M is the magnetic quantum number. This magnetic quantum number m, depends upon spin quantum number I and takes the values from minus I to plus I. So these defines the directions of quantization. The quantization is defined by number minus I to plus I. Now, if you want to know the quantization directions for spin half, we got minus half and plus half, only two. Similarly, for spin 1, the quantization directions were minus 1, 0 and 1. We also found out the angle of the directions of these vectors, of the quantization directions. We also worked out the angle, we got its magnitude. From today, we'll go further. I'll introduce another parameter, another term called nuclear magnetic moment mu. This is defined as mu. We will start like this. What is nuclear magnetic moment? If you have a charged nucleus rotating with some angular velocity omega, which I know is equal to 2 pi into frequency nu, then it creates a magnetic field. We know that charged nucleus rotating with angular velocity gives a magnetic field. This is the let us just charged nucleus as spin, which is rotating, undergoing precession. So it has to create a magnetic field. So it is analogous to a small bar magnet with two poles, north and south pole. So that means you can interpret this spin as a small dipole. It is a small tiny magnet. This is analogous to bar magnet whose axis is coincident with the spin rotation axis here. Now, as a consequence, we can say nuclear spin is like a tiny magnet. When I say nuclear spin behaves like a tiny magnet, we can define magnetic moment also. And this, since it is a dipole having two poles, north pole and south pole, similarly, it is analogous to a small bar magnet. This spin has a dipole moment. It is called magnetic dipole moment, which is represented as mu. And mu is a vector. Remember, I'm introducing few terms. First, we started with angular momentum P. We found that the this z component of that Pz, which was equal to m into h cross. M is magnetic quantum number, which depends upon spin quantum number I, which I said is mi. I is equal to, let us say, the spin of the nucleus. Then mi means magnetic quantum number goes from minus I to plus I. So those were the three terms. Now this is a magnetic moment, mu. Is another term which I am introducing. Please don't get confused with the terms which I am repeatedly using and changing. So mu is a vector. The magnetic moment mu is proportional to angular momentum P. Remember, the magnetic moment is proportional to angular momentum P, and the proportionality constant is given by a term called gamma. Gamma is gyromagnetic ratio. It is constant for a given nucleus. Gamma is constant for a given nucleus. It has some units. In the SI unit, gamma is expressed as radians per second per Tesla. This is the unit of gamma, radians per second per Tesla. So please remember the magnetic moment, which I said just now introduced the term, is proportional to spin angular momentum by a constant proportionality constant gamma. Now we knew what is P. I worked out. P we also got. P is equal to h cross into root of I into I plus 1. Remember, very first slide when last class or before last class, when I introduced magnetic angular momentum P, I worked out and I said P is equal to h cross into root of I into I plus 1. Substitute for that P in this equation now. Now this mu becomes mu is equal to h cross into gamma into I into square root of I into I plus 1. All I did is I substituted for P in this equation. That's all. Now what happens if I is equal to 0? There is mu becomes 0. There is no magnetic moment. Remember, magnetic moment is important. When you have a magnet, you have a magnetic moment, because as you go ahead, I'll tell you the interaction of this magnetic moment with the external field is required to observe NMR. That means if I is equal to 0, mu is equal to 0, no magnetic moment, no NMR. That will come later. Now coming back to gamma. Gamma is a constant for a given nuclei. Gamma values have been experimentally determined. For example, for proton, its value is 26.753 into the 10 to the power of 7 radians per Tesla per second. Remember this value. Very often we require this. Similarly, for carbon 13 isotope, value of gamma is 6.728 into 10 to the power of 7 radians per Tesla per second. You may also notice one small important interesting thing here. The gamma of carbon is nearly 4 times smaller than that of protons. Gamma of proton divided by 4 is nothing but the gamma of carbon approximately. This you keep it in mind. I need to stress upon this again because I will be using this term very often in the subsequent classes. Now angular momentum P, I said, is quantized and mu is also quantized. So because angular momentum vector we calculated its component along z-axis and we had a quantization directions also. So as a consequence, mu is also quantized along z direction. So in the presence of an external magnetic field, like P is quantized, P is related to mu, okay? Mu is equal to, we just now worked out here, remember, mu is equal to gamma into P. Because P is quantized, mu is also quantized, okay? So we can write Pz component we knew. We worked out Z component with the angular momentum Pz is equal to h cross into m. Now if I have to get a mu Z component, it is simply equal to gamma into Pz because mu is equal to gamma into P. So Z component of is similarly mu Z equal to gamma into Pz. All we have to do is to substitute for Pz, which is h cross into m, that we have been working out. We calculated Pz, magnitude, everything, remember earlier. So it is nothing but mu Z equal to gamma into h cross into m. Its value also depends on a magnetic quantum number m. So what next conclusion is, we introduce the term mu, magnetic quantum number, which is because of when we were understanding angular momentum, and we came to know it depends upon magnetic quantum number m. So the magnetic moment depends upon magnetic quantum number m. So mu is a magnetic quantum number. It depends upon, magnetic moment. Mu is a magnetic moment. It depends upon magnetic quantum number m. Please understand. So we have come to some level where we have understood angular momentum P was quantized. We got the Z component of angular momentum, which was quantized. We understood the direction of quantizations. And then afterwards, we introduced the term mu. We know mu is equal to gamma into P. That was the equation I gave you. Because mu is proportional to angular momentum, proportionality constant was gamma. Since this is quantized, mu Z is also quantized. So Z component of magnetic moment is also quantized. And that quantization, as I said, depends upon magnetic quantum number. So simply you understand Magnetic moment, the direction of quantization again depends upon magnetic quantum number. That is the conclusion you must remember. Now, we introduce the constant of proportionality called gamma. What does gamma depend on? How do you get the value of gamma? Of course, magnetic ratio you can work out. It depends on the charge and mass of the nuclei. If you know gamma, it is equal to E over 2 into mc. E is the charge and m is the mass. Of course, you know the C. So now, simply, you can understand from this equation a logic. Nuclei with higher mass have lower gamma. Remember, mass comes in the denominator of this equation. As you go to higher and higher nuclei in the periodic table, mass keeps on increasing, gamma value keeps coming down. It is a very important parameter, remember, gamma. So nuclei with higher mass always have lower gamma. Remember, in one of the previous slides, I showed gamma for proton was 26.75 into 10 to the power 7 radians per Tesla per second. When I showed for carbon, it was 4 times less, because carbon 13 mass is higher than that of proton. As a consequence, gamma was 4 times less. Okay, now you understand. Among all the stable isotopes of elements in the periodic table, proton, that is the hydrogen atom, has the lowest mass and has the highest gyromagnetic ratio. Please remember my statement. I use the statement stable isotopes. Why I use the stable isotope? You can consider tritium. That is a different. So the tritium, the isotope of hydrogen, it is something different. But that is a unstable this thing, but it has a different gamma. I will not go into the details, but please understand that is a higher resonating frequency compared to that of proton. But among all the stable isotopes, proton has the lowest mass and has the highest gyromagnetic ratio. Okay, and gamma is the constant for a given nucleus. That is known. And different nuclei have different gamma. I said gamma is only constant for a given nucleus, but different nuclei, different isotopes change, have their different masses. As a consequence, gamma has to be different. So different nuclei have different gamma because of their mass. So now if you go by this equation, mu z equal to gamma into pz, it is equal to gamma into h cross into m. So mu z has different values for different nuclei, even though they have the same spin quantum number I, same magnetic quantum number m. Please understand this. Don't get confused. Mu z equal to gamma h cross m. That's what I wrote earlier also. When we substituted for pz, which is equal to h cross into m, we know what is mu z. Now, m depends upon I. So that means consider two nuclei. Let us say it has same I, and it may have a same magnetic quantum number because I is same, but mu z can still be different. Mu z has different values for different nuclei, even though I is same and m is same. I'll give you an example now. Consider proton and carbon 13. Why they are different? Because as far as the spin quantum number is concerned, I, spin quantum number, is same. Both are spin half nuclei. What is magnetic quantum number for both of them? M. That is minus 8 plus 8 will take. Both have same quantum numbers. M is same. Magnetic quantum numbers is same for both nuclei. Then what makes it different? I said mu z is different for different nuclei. That is because, remember, gamma is different due to mass. As a consequence, mu is different. That's what makes proton and carbon different because of their masses. So what is different is, although two nuclei, proton and carbon, have same spin quantum number, same magnetic quantum number, The gammas are different, consequent to different masses. As a consequence, what happens? Mu is different because gamma is different. Mu is equal to gamma into P. So mu is different. So carbon 13 and proton have different magnetic moments. It's a very important point. They have different magnetic moments. So let us see some characteristics of the different nuclei. I have made a list here. Let us go through a couple of them. There are five columns, several rows I have put, different nuclei with their properties. Concentrate on proton. Proton is a hydrogen isotope. I am considering proton. Natural abundance is 99.98, almost 100%, close to 100%. It is spin half nuclei. Its magnetic moment is calculated already. We know how to calculate experimentally. But its gyromagnetic ratio gamma is 26.75 into 10 to the power of 7 radians per Tesla per second. That I have been repeating. I told you earlier also. Now look at the same thing for deuterium. It's a very small abundance, 0.0156. Spin is 1 and gamma, you see, is much, much smaller. About 6.5 times smaller than that of proton. On the other hand, look at carbon 13. This is another nuclei which is extensively studied by chemists and biologists. Everybody, all of us study apart from proton, carbon, nitrogen, others are very favorable nuclei for us. That is interesting. Look at this natural abundance of carbon, 1.108. Again, spin is equal to half, but gamma is nearly four times smaller than that of proton. Next, abundant spin, which is favorable to study, is fluorine. Look at fluorine, 100% abundance, spin half nuclei. And look at the gyromagnetic ratio, almost close to that of proton. And please understand, look at this thing, because I'm going to tell you later, this gamma is a very important parameter for defining the sensitivity of the nuclei. And abundance is another thing which is also important in detecting the signal. That's why I'm stressing on these two columns, natural abundance and gyromagnetic ratio. And of course, spin is an important thing. So that's why I've concentrated on the deuterium, carbon, and fluorine, all the three nuclei. So, which is the nuclei with higher gamma apart from proton? Next is fluorine. Among the nuclei which are well studied, which is generally in demand apart from proton afterwards, more investigated, is carbon 13, which is spin off, gamma is 4 times smaller. Let us keep this point in mind. Of course, some of the times biological studies and are in some other studies, phosphorus is also extensively investigated. Again, it is 100% spin-off nuclei, but you see, gamma is nearly 2.5 times smaller than that of proton. These are some of the interesting nuclei: proton, carbon, fluorine, phosphorus, and sometimes for inorganic molecules and others, you can study silicon also. No problems. What I wanted to say here is, they all have different gammas. Though it is fluorine and proton have nearly equal values, but there is a difference. No problem for us. That small difference is enough. What it means is, all nuclei with a different gamma can be individually investigated. All nuclei in the periodic table, if you look, if they have a different gamma, they can be individually studied. What does it mean? In the periodic table of elements, you can see lot of elements. Every element, at least, there is one isotope which has I, and all these elements have different gammas. So everything can be individually studied. Whole periodic table can be studied by NMR with individual nuclei. But if you look at it, commonly investigated nuclei in chemistry and biology are proton, carbon, nitrogen, phosphorus. All are spin half nuclei. And this is abundant. This is highly abundant. Of course, these two are less abundant spin, but more explored. These two are very well utilized. And of course, deuterium in many examples of hydrogen deuterium exchange studies, etc. And direct detection also we use. These are spin 1. So spin half nuclei are relatively easy to study. Spin half nuclei are very easy to study. Remember, I always stress upon this. Our main focus of this course is to study, understand spin half nuclei. Spin 1 nuclei are spin greater than half are all quadrupolar nuclei like 11b, boron 10, aluminum, oxygen, silicon. Many of them are studied in inorganic chemistry and material science. They require people do extensive studies of boron, silicon, aluminum studies in borosilicate classes, aluminosilicate classes, and zeolites. Varieties of materials are there where such nuclei are also used to study their properties, structure, conformation, etc. That's also there, but they are all spin greater than half, of course, except silicon. And here, these nuclei are most often used in chemistry and biology, except deuterium, all are spin half nuclei. Please remember this extensively. We use it when we analyze the spectrum later. Many of these examples I will take. Next, another important point I want to stress is interaction of nuclear magnetic moment, that is mu, with the external magnetic field is the basis of NMR. Remember, for NMR, we require a very strong magnetic field. All you have to do for doing the experiment is you have to take your sample, put it in a magnetic field, which is huge, whose strength is of the order several tens of Tesla, 10 Tesla, 15 Tesla, 20 Tesla of that order. What is a Tesla? 1 Tesla is a 10 to the power of 4 Gauss. Very high magnetic field. Such an external magnetic field is required for NMR. So all you do is you take your sample for investigation, put it in an external magnetic field. This external magnetic field is conventionally referred to as B naught, B subscript 0. It is referred to as B naught. Now, what happens if you put your sample in a magnetic field? There is an interaction. So, simply, if you put the sample in a magnetic field, you cannot get NMR. There is a reason for it. The reason is the nuclear magnetic moment mu that we just now discussed. It will interact with the external magnetic field, and that is the basis of NMR. Okay. So, nuclear spin quantum number I must be non-zero to detect NMR. That's what we observed. Okay. We just now observed mu depends upon mu depends upon magnetic quantum number m, which depends upon I. Just now we understood. So I must be non-zero. We saw that when we calculated mu, when I is equal to 0, we wrote mu is equal to gamma into root of I into I plus 1. When I is equal to 0, mu was 0. That's what I said. When a magnetic moment is 0, when I is 0, magnetic moment is 0. When the magnetic moment is 0, then such nuclei cannot interact with the external magnetic field. Please understand. So mu must be non-zero. For that, I must be non-zero. Then only we can detect NMR. So that is the reason why I said when the very first class, when I wrote a table to work out the spin of the nuclei based on their atomic mass and atomic number, I gave an example of carbon 12 whose spin is 0, I equal to 0. I said it is NMR inactive. That is the reason. I was 0. So when I is equal to 0, mu is 0. When mu is 0, this nuclear magnetic moment cannot interact with the external magnetic field. As a consequence, you cannot see NMR for carbon 12. Now, this tells you one spin must be present, I must be non-zero to see NMR. So, this is an important concept. I hope you are understanding. Different nuclei with a different gyromagnetic ratio have different mu. They all have different interaction strengths with the external magnetic field. So, since mu is different for different nuclei, because gammas are different, when the mu interacts with the external magnetic field, strong magnetic field, which you put it, they have different interaction strengths. As a consequence, The interaction of the protons with the external magnetic field is different. Similarly, the strength of interaction of the carbon with the external magnetic field is different. This is what makes the difference. As a consequence, we can observe different nuclei individually because their interaction strengths are different. If they were same, then you would not have seen the NMR of different nuclei. So this is a beauty because gammas are different, mu's are different. Because mu's are different, interaction strengths are different with the external magnetic field. Okay, this is important point. So when magnetic moment of the nucleus interacts with the external magnetic field, what happens? I said interaction is essential. Okay, magnetic moment of the nucleus is interacting with the external magnetic field. That's fine. So what happens? Next question. Important thing is the nuclear spins, which are tiny magnets, start aligning in the static magnetic field. Remember, if I say nuclear spin, tiny magnet, magnetic moments, these are the same terms which we use interchangeably. Don't get confused at all. If I say interaction of the magnetic moment, it's nothing but the interaction of the nuclear spin. Okay, it is nothing but the interaction of the small tiny magnets. All are interchangeable words we keep using very often in NMR. Don't get confused. So interaction of the nuclear spins or the magnetic moment means the nuclear spins start aligning in the static magnetic field. Or in other words, magnetic moments start aligning in the magnetic field. You get the point. The nuclear spins start aligning in the static magnetic field. How do they align? Some align in the direction of the field, some in the direction opposite to that of the field. How should it happen? See, we say interaction of magnetic moment with the external magnetic field have different energies for different nuclei. That's correct. But now I am telling you further, this new magnetic moment mu have quantization directions that we observed. And what is happening is some of the mu's orients in this direction, some orients in the opposite direction, and they have again different energies. You understand? Nuclear spins which align in this direction, in the direction of the field, and those which align in the direction opposite to the field have different interaction energies. Is it not? NMR is very interesting to understand. We understood I because of mu is because of m is because of I is there, and mu interacts with the external magnetic field, which is different for different nuclei because of different gamma. But how it interacts, I said, nuclear spins start aligning because the quantization directions are known. As I said, some orients in this direction, some orients in the direction opposite to the field. For spin of nuclei, I am considering. And these further have different energies. Energy of interaction for the spin or the magnetic moment in the direction of the field is different from the energy of interaction of the magnetic moment in the direction opposite to that of the field. So that means we have two energy states. When I said what happens because of the interaction of the magnetic moment with the external field, so what? It interacts. How does it interact? This is the consequence of that interaction. The consequence of that interaction is these two energy states, which are two different energies for orientation along the direction of the field and opposite to the direction of the field, they get separated out. This is called Zeeman effect. It's a very well known thing. You all of you must have understood and studied in some spectroscopy. This is called Zeeman effect. Zeeman effect is nothing but interaction of the magnetic moment with the external field. It's the largest interaction strength among all the external interactions, or including some of the internal interaction apart from large quadrupole moment and nuclei. Among all the interaction strength, especially external interaction, Zeeman interaction is the largest strength. Okay. Next, we'll understand. We'll understand mathematically how these two are interacting. Consider spin half nuclei. I have two quantization directions, two orientations of the magnetic moment in plus half and minus half. Okay. The interaction energy, I said there is an energy of interaction because of magnetic moment interacts with B naught. It is both of them are vectors. Mu is a vector, magnetic field is a vector. And the interaction takes place and it is a dot product. Okay. Now, in the absence of the magnetic field, all these orientations are random. There is no preferred orientation at all, preferred direction of orientation for any of these magnetic moments or nuclear spins. There is no preferred orientation. Moment to put this in the magnetic field, what happens? Okay, before that, let me tell you, that means there is no when there is a there is no preferred direction of orientation, all are equally powerful, they are random distribution. That means these energy states are not separated out in the absence of the magnetic field. That is why they are called degenerate states. Degenerate means these energy states are not separated in the absence of magnetic field. There is no separation of energy states. They are called degenerate states. Now, moment to put it in the magnetic field, the degeneracy is removed. That's what I said. The interaction energy in the direction parallel to the field, in the direction opposite to that of the field, they have different energies. As a consequence, there is a spins orientation changes. It is not. It is now randomly distributed. As I said in the previous slide, there are some spins orient in the direction of the field, some orient in the direction opposite to that of the field. This is exactly what happens. This random distribution was there in the degenerate state. Now there is a preferred alignment of the nuclear spins in the direction of the field, in the direction opposite to that of the field. This is called removal of degeneracy. What happened now? When I put the magnetic moment in a magnetic field, nuclear spin in the magnetic field, the magnetic moment interacted with the external field. As a consequence, the energy states get separated out, causing because of removal of degeneracy. This has one energy, this has one energy. And the difference between this is called delta E. That is the difference of energy. Okay. Now, if you understand here in this equation, I have put minus interaction energy. What do you mean by energy negative? Why I have put a minus? There is a reason for it. Please understand. Reason is it is to ensure that spins are oriented in this direction of the external magnetic field has lower energy. Remember, in this, those spins which are oriented in the direction of the magnetic field, parallel to the magnetic field direction, have lower energy. This has lower energy compared to this one. The higher energy state is the one where the spins orient anti-parallel to the magnetic field. Lower energy is the one where the spins orient parallel to the magnetic field. To bring in this concept, negative sign was put in this equation. You understand? Okay. Now we can understand more about the energy of interaction, and we can resolve them into different components and find out what is the energy for each of the states and get the energy difference between them, calculate the energy difference between them, and then calculate the frequency of that. Lot more things, little bit of conceptual understanding is required. We can do that. What I will do is, I will stop for the day. We'll come back in the next class. We'll continue from this. Now we have understood in this class what is magnetic moment and how it interacts with the external magnetic field, where the degeneracy is going to be removed because of the interaction of these tiny magnets, nuclear spins, which I call as well magnetic moments. With a big magnetic field, degeneracy gets removed. Some orients in the direction of the field, some orients in the direction opposite to that of the field. This interaction energy was given by E equal to minus mu dot B. It's a dot product. Both are vectors. And this is the energy general equation I gave. Now we calculate the energy for each of the orientations and get the frequency so that we know what is the frequency and how we get NMR. Everything we'll discuss in the next class.